Hey, and welcome to another video from Hegarty Maths. It's Mr. Hegarty here, and this is our first video in Core 2 on differentiation. And in this video, we're going to be talking about increasing and decreasing functions. Now, if you're in any way not up to scratch on your differentiation, please look back at the Core 1 differentiation videos. Those skills must be solid before moving on to this section at all. Right, let's start. And I'm going to be kind in the sense that I'm going to do a tiny recap. But if this is alien to you, you must go back to the Core 1 videos. Here's my question. What is differentiation about? Can you remember? Well, what differentiation does, hopefully you know this, differentiation allows us to work out the gradient of a curve at a particular point. Now, unlike straight lines where you could work out the gradient, it's constant. Like, if you've got a straight line, think about it like this. The gradient is just constant all the way. In a curve, the gradient is always changing. For example, here, from here to here, the gradient you can see is positive because as you go across the x values, you're going up. Whereas at the very top here, the gradient looks negative, and along here, the gradient is going down, the curve's going down, so it must be negative. Here again, it looks like it's 0, and here it goes up, is a positive number here. So the gradient is changing at each different point along the curve, and differentiation allows us to work out the gradient of a curve at a particular point. How do we define the gradient of a curve at a particular point? Well, hopefully you know what this here. So the gradient of a curve at a point is defined to be, by definition, so I'm going to write is defined to be the gradient of the tangent to the curve at that point. So hopefully that's familiar to you as well. So if I wanted the gradient here, it's going to be equal to the gradient of a tangent that I drew to the curve there. Remember, a tangent is a straight line touching the curve. Whereas if I wanted the gradient, let's say here, I would have to draw a different tangent here to the curve. So the gradient by differentiation is equal to the gradient of those tangents of the curve. And remember the following: if I call my function y, right, my original function, do you remember what my gradient function, how does it look? My gradient function is given the notation dy by dx. Alternatively, if I call my original function f of x, I can call it both ways. Can you remember what my gradient function is? Well, it's f dashed x, means my gradient function. Okay? And that's a basic summary. So let's go straight into this chapter now. I'm not going to remind you of differentiation, how to do it with polynomials. You're just going to have to pick that up as you go along or watch the other videos. Let's go straight into what an increasing function is. We need to know this, so copy these definitions down. I'm going to draw a graph, and I'm going to draw a function for you here, and call that y, or is equal to f of x. And I'm telling you that's an increasing function. Could you explain to me what you think I mean by saying this is an increasing function? Okay, so we're going to write down an increasing function is one where as x increases, y increases. Simple as that. As you go along in that direction, you end up going up as well. Okay? That's an increasing function. So you just need to know that. We also need to know what a decreasing function is. So on the next slide, could you think of drawing a picture for a decreasing function yourself and give it a definition? I'm going to go through that now in 2 seconds, so just have a think. Well, I think that's fairly straightforward if you know what an increasing function is. A decreasing function is going to be one that does something like this. So a decreasing function is one where as x increases, y decreases. Okay, so as you go along here, you end up going down. Now I'm just going to go to dual page just quickly. They're my two definitions of an increasing and decreasing function. There is something you can say about the gradients of each of these. I wonder, could you tell me something about the gradient of this one? And could you tell me something about the gradient of this one? Well, think about it. If I work out the gradient at any point here, look, I'm drawing random tangents to it. Can you tell me what type of number the answer would be if I worked out the gradient? Well, for an increasing function, the gradient is positive. Okay? Or you could say the gradient function is positive. Gradient function. So that's f dashed x or dy by dx, depending on what notation they've used, is bigger than 0. Now, what do you think you can say here about a decreasing function? Well, you can say that the gradient is negative. And so you could say that f dashed x is less than 0 or dy by dx is less than 0, depending on the notation they use. Okay? So hopefully you can see that in those cases. Now, sometimes a function can be increasing and decreasing in different sections. So hopefully you can see that along here, okay, it's different from up here, it's different from along here, it's different from here, and it's different from here. I'm going to give these points various names. I'm going to imagine this point here is, let's call it x1. This point here is x2. This point here is x3. And this point here all the way to the end is going to be x4. Now, for any x number between x2 and x1 along here, it's an increasing function, isn't it? So we have an increasing function, i.e. dy by dx is bigger than 0. At this point here, at this very tip point here, dy by dx equals 0. For anything x number between x3 and x2, we have a decreasing function. It's decreasing. So we have dy by dx is less than 0. For this exact point here, dy by dx equals 0. And for any point between x4 and x3, we again are back to increasing function. So we have that dy by dx is bigger than 0. Or we could have called these f dashed x. Okay? Now that's the introduction to increasing and decreasing functions, and it's also to show you that at different points a curve can be increasing and decreasing at different sections. Right, I'm going to do two simple examples for you, and I'm going to show you how these style of questions come up. Here's example 1. Let's copy this down. Show that the function f of x is equal to x cubed plus 24x plus 3 for x belongs to the real numbers is an increasing function. Now this just means here, this sign means belongs to, and this sign means real numbers, and it just means the number line is a number. So this just here in essence just means x is some number. Okay? So show that the function f of x is x cubed plus 24x plus 3 for some x number is an increasing function. Now, what you need to know, the fact you need to know about an increasing function has f dashed x, its gradient function, bigger than 0. That's what an increasing function has. So we have f of x. Remember, f of x is equal to x cubed plus 24x plus 3. Remember, that's like x to the power 1. So we could work out f dashed x. Let's work out f dashed x. So we're going to bring down the 3, keep the x, reduce the power, plus bring down the 1, keep the 24, keep the x, reduce the power, plus numbers differentiate to 0. So f dashed x with a bit of tidying up is going to equal 3x squared plus 24. Now, if we can show that f dashed x, the gradient function, is positive, we are showing that the curve has a gradient that's positive. We are showing it is increasing. It therefore must be increasing. So we just have to prove, this is what we have to show. We must show f dashed x is bigger than 0. Can we show that? Well, actually we can. Let's think about why. X squared is a very special thing. It's a square number. So we know for a fact that x squared is bigger than or equal to 0. It can equal 0 if x was 0, but otherwise any number, it will be bigger than or equal to 0. So certainly, therefore, we can say that 3x squared, 3 lots of x squared, must be bigger than or equal to 0. And therefore, we can say that 3x squared add 24 must be actually bigger than or equal to 24. Because if this thing here is bigger than or equal to 0, something bigger than or equal to 0 add 24 is 24 or bigger, isn't it? So therefore, we know that f dashed x is bigger than 0 for all x. Doesn't matter what x, therefore f of x, the original function, is increasing. The original function is increasing if its gradient function is positive. Done. Okay, let's have a go at example 2. Example 2. Find the values of x, alright, find the values of x for which f of x is x cubed plus 3x squared subtract 9x is decreasing. Now that assumes to me that it's not decreasing for all x. There's going to be some places it's increasing function, some places the gradient function equals 0, and some places it's a decreasing function. For the sections it's decreasing, this must be true. So let's think. What must be true where it's decreasing? Where f of x is decreasing, its gradient must be negative. F dashed x must be negative for those points. So because we know f of x is equal to x cubed add 3x squared subtract 9x to the power 1, we can work out f dashed x, which bring down the 3, keep the x to 1 less power, plus bring down the 2, keep the 3, keep the x to 1 less power, and then bring down the 1, keep the 9, and x to the power of 0. And tidying that up, f dashed x must be equal to 3x squared plus 6x subtract 9. Now, we want to find, think about it, we want to find where the function is decreasing, so we want to find where its gradient is 0. So what we want to solve f dashed x is less than 0. So let's try and solve it. Let's solve 3x squared plus 6x subtract 9, which is f dashed x, is less than 0. Now in core 1 we did so much work on how to solve a quadratic inequality. You factorise, which factorises like that. You then draw this graph. Now this is not your original graph. This has got nothing to do with this graph here. Remember, you are solving some algebra here related to this problem. This is not this graph. This is some algebra relating to the problem. So we're going to draw that graph because it's just going to help us get our x's in the right place. We've got a root at -3. We've got also a root at 1. It's a positive U shape, so it's going to look something like this. And we want where the graph is less than 0, so we want this bit. I'm sure you can see this bit here. So we therefore know what the values of x are going to be. X is therefore some number between 1 and between -3. And for those values, this thing is less than 0, therefore this thing is less than 0, Therefore, f dash x is less than 0 for these numbers. And therefore, for these points, f of x, the original function, is decreasing. And that is the answer. So therefore, we'll just state, therefore, for negative 3 less than x less than 1, for those x values, f of x is decreasing. And we are done. So thanks loads for watching. Hope you found that video useful.